This is part 2 of Faraday's law. What I want to consider today is an induced EMF and the electric fields that come as a result of that. So I can create an electric field in a conductor as a result of a changing magnetic flux. This is different than the electrostatic fields that we studied at the beginning of the course, caused by point charges or charged objects. So even in the absence of a conducting loop, a changing magnetic field will generate an electric field in empty space. Unlike the electrostatic field, though, this field is not conservative, so there's not a potential associated with this field. So it's not like the field produced in the electrostatic case. We can express this EMF as the line integral of E dot ds over the path, and therefore we can rewrite Faraday's law in a more suggestive way as such. The integral of E dot ds, that's going to be the EMF that's produced, is equal to minus the change in magnetic flux with respect to time. This is another way of writing Faraday's law. And you might say, well, what would that electric field look like if I were to calculate that using Faraday's law? Let's do an example of that. Suppose I have a conducting loop like such. It's got a radius r, and I'm putting it in a constant magnetic field going into the blackboard. So I'm going to induce a current if I let's think about this. Suppose I have charges in this conducting loop. Notice what's happening. If I move a test charge around the loop, notice that the work done in moving that test charge around the loop is Q times the EMF that it would take to make it go around the loop. So it's a charge times a voltage, if you would, from our previous work. So I can say that the work done, since the force on the charge is Q times an electric field, the work done would be the force times the distance that I've moved the charge around the field, which is 2 pi r. And so I could write that as I have it, Q times the electrostatic, the EMF that's induced. Therefore, the electric field, if I cancel the Q's, I could just express as the EMF divided by 2 pi r. Take it a step further, the magnetic flux that's associated with this loop, E sub B, would be equal to the magnetic field, the constant magnetic field, times pi r squared. And so I could write my electric field and put all this stuff together as minus 1 over 2 pi r d phi dt, or in this case, minus r over 2 dB dt. So you can see very plainly in this very simple example that a changing magnetic field produces an electric field. So we have another way of writing Faraday's law, which is integral of the electric field around the loop is going to be equal to minus the change of magnetic flux with time. And this is a nicer way of expressing Faraday's law, because what we're interested in is how changing magnetic fields cause electric fields. We'll find out later that the opposite is true too, although it may not be obvious at this moment. Let's do one example of this to kind of finish out what I'd like to talk about. And that is the electric field due to a solenoid. So suppose I have a long solenoid, very, very long solenoid of radius r and number of turns n, and it has a current that varies with time. So I'm going to write it as I naught times the cosine of omega t. Suppose I want to find the magnetic field, find the electric field at some distance little r outside the solenoid. So some distance r from the center of the solenoid. I want to find the field at this point. That's induced by this changing, I have a changing current, therefore that's going to cause a changing magnetic field, which will cause a changing magnetic flux, which will induce an EMF and also cause an electric field. Let's look at that. Well, first off, by Faraday's law, I know that integral of E dot ds is going to be equal to minus d phi dt. I can write this, the magnetic field for a solenoid, the area of the solenoid isn't changing, so that's just going to be the same. I'm going to write that as the field, though, for a solenoid is mu naught times I times the number of turns divided by the length of the solenoid. And therefore, I'm going to, suppose we have we'll give this solenoid some length L. We can also write this as mu naught I times little n, where n is just the number of turns per length. So we'll use that for our magnetic field. The area element, though, if I want to find the magnetic flux, the area element is going to be equal to mu naught I n over L times 2 pi r dr. So that's the area element for the solenoid. So this whole integral will give me